Welcome to the next session on instrumental analytical chemistry, where we talk about UV-vis spectroscopy, solvent and conjugation effects. So really today we're going to be going beyond the fundamentals that we encountered in the previous lectures, where we were concerned with things like how does an absorption process actually happen? What are some of the components in my UV-vis spectrometer so that if ever anything goes wrong, I'll be in a position to help in the fixing of that problem, and at least I'll have an idea of what is required and what is necessary. Now we're going to be looking at what happens whenever we choose different solvents for our analyte, because oftentimes we're working with liquid samples, or we have dissolved our solid sample in a solvent in order to measure it. It's usually quite difficult to measure solid samples in the UV-vis spectrometer. Often you need a special type of equipment. But it is possible, but generally it's not done. It's usually done liquid or sometimes gas absorption measurements. So we have to choose some sort of solvent. So the solvent choice is going to be important because some analytes don't dissolve in some solvents and they do in others. And the choice of solvent can affect the quality of the spectrum that we get out. Then we also have something called conjugation effects, which can change the way in which the spectrum peak is found, like where the lambda max is found and so on. So samples in the UV, a little bit of revision from last time. So which samples can be detected? Basically, we usually have a transition of pi to pi star or n to pi star as being our kind of usable ranges. So the ranges over here, so these ones, the n to pi star, the pi to pi star, and sometimes the n to sigma star, but usually it's these two, the ones going to pi orbitals. They're the most accessible, lowest energy, and least destructive. We cannot usually measure the sigma to sigma star, so going from here to here, because what actually happens is it destroys the molecule. So this is a simple diagram of what's called a molecular orbital diagram. So this is representing the orbital from the carbon atom, and this is representing the orbital from the other carbon atom here and here. Now, each one of those is sharing an electron in its covalent bond. And so it forms this bonding orbital. And this is stabilizing because it is lower in energy than the individual carbon atomic orbitals. However, if we were to have an absorption process here from sigma to sigma star, what would happen is that one of the electrons would go into the topmost orbital. This is an anti-bonding orbital. And what would happen is that there would no longer be sharing of two electrons between the two carbons, thus forming a covalent bond. Instead, we now would have only one electron here and the breaking of this covalent bond. So certain transitions can actually destroy our molecule. So the transition that we've seen here is destructive to the molecule, causing cleavage of the sigma bond. And so those sorts of transitions cannot be measured. They're oftentimes in the vacuum UV as well, so it's a little bit hard to actually produce light of that wavelength to actually measure them. So usually, like, there's only a certain range of materials which can actually be measured reliably. But thankfully, usually the molecules we want to measure, our analytes, fall within that range, and usually the molecules we don't want to measure, like our solvents, don't fall within that range. So usually it's the blue and the green. Sometimes it's the purple, never really the red. So solvent effects, so we saw this as well last time. Solvent effects have a big effect. So we can see here the same molecule, this cyclic amine amide structure. And this has been dissolved in three different solvents. You can see two different solvents. One is the vapor phase or the gas phase. One is hexane solution, and the other is aqueous solution. And you can see here, hopefully, the effect of adding a solvent has made the peaks broader, and then adding a more polar solvent has made it even more broader. So the non-polar solvent hexane is an alkene. So you might have remembered that from any organic lectures you've had, just chains of carbon and hydrogen atoms. And then here, aqueous solution is dissolved in water. We have a very broad peak. There's no real fine structure here. You could not use this for any kind of qualitative measurement, but you could still use it for quantitative measurement. There's still like a peak here. So that's good. So the choice of solvent has a big effect. Solvent effects make UV better for quantitative measurements rather than qualitative, i.e. identification experiments. So, pardon me, it's not really very easy to find exact peak positions. Because if we do it in solvent, you can see that a lot of the peak structure here has been lost. Whereas if we do it in aqueous solution, we totally lose any idea of having peak positions, but we still have a maximum somewhere. And so that maximum will be consistent regardless of concentration. And so that's why we're able to use this very much quantitative measurements, i.e. finding the concentration, rather than qualitative identification. So we're not really able to identify what molecules we have using UV vis. It is possible, but there are better techniques for it. You could, if you were really, really needing to qualitatively analyze your system, but most of the time it's done for quantitative, and that's because of the ease of these measurements and the high throughput. I mean, it doesn't take very long to measure these samples. You get an accurate measurement of peak absorbance and things like that. So it's really good for quantitative measurements, not so good for qualitative. Solvents can also absorb UV vis light, so we need to choose one that does not overlap with our sample, so it is transparent. So so solvents are also molecules. They have bonds. They have the ability to absorb light. So we have to choose solvents which will not overlap with the sample. So polar solvents usually destroy the vibrational fine structure. So the vibrational fine structure is the vibrational energy levels, which are, the lower energy levels surrounding the electronic energy levels. So if we have the electronic energy levels, so for example, first, and then we have another one up here, the excited state, then we have like, excuse my terrible line drawing, but we have these like lower energy lines here, and those are the vibrational energy levels. Those contribute to what's called the vibrational fine structure. And so that's why we have the sharp sort of like jagged lines. So the more polar your solvent, the more likely it is to destroy this, because the polarity allows the transference of this energy much more easily than non-polar molecules do. So the gas phase here, we can see that it has very good fine structure. But if we put it in the heptane solvent, the peak positions are in the same position, but you can see now it's much broader. Gas phase, you've got clear peaks. Heptane solvent, it's much broader. You can actually still see the peaks in the heptane solvent. Let's not kid ourselves, you can see it, but it's a lot harder to see. Then in water and alcohol solvents, we've got a different system here. You can see that there is going to be a certain degree of destruction of the fine structure. So you just basically have a continuum, one broad peak. And here are a number of wavelength maxes, which are where the maximum absorbance of our different solvents might be. So water is a common solvent, ether, diethyl ether, methanol, ethanol, chloroform, carbon tet, benzene, THF, tetrahydrofuran. These are all common solvents, especially like things like ethanol and water and diethyl ether. These are the lambda maxes. These are the peak positions of these solvents. So you don't want to be having an absorbance of your analyte near the peak absorbance of your solvent, because otherwise you're going to be having a difficult time determining which one is your solvent and which one is your analyte. So non-polar solvents most likely to give gas phase like data, and solvent can change the position of the maximum. So yes, that's what's going on here. You can see that the water solvent and the alcohol solvent have given different peak maxima for our measurement. So as well as that, the solvent also produces something called a measurement window. So this is related with the reduction of vibrational fine structure in the previous slide, but here we're now talking about what is the range within which we can actually measure our samples. So solvents can also have absorbance ranges, as we talked about. They are, after all, molecules with bonds and atoms. They must be transparent, i.e. have no absorption in the desired range, i.e. the measurement window. So we don't want there to be a strong absorbance from our solvent at the same peak position or even close to the same peak position as our analyte, because then we just won't get a reliable result. And so some cutoffs are shown opposite. Measurement below this wavelength are not reliable. So basically, this is the, imagine for acetonitrile, anything from like, I don't know, 1 nanometer up to 190 nanometers would not be a reliable measurement, but we could measure, 200, 250, 300. You could measure anywhere in the visible and it would be okay. Chloroform then, something similar, hexane, dioxane, and what have you. These all have really strong absorbances in the high energy UV around about 200. So anything your analyte would measure around there is not going to be any good. But there's sort of like I guess a visual check you can do. Remember that we as humans have a visual range of wavelengths that we can see. So if your measurement of your analyte is going to be in the UV and your solvent is also colored, then you're probably not going to be able to measure it very well. So if your analyte is in the visible range, it should have a color. It should be colored in some way. Maybe it's yellow, maybe it's red. That's an obvious indicator that there's going to be a peak position that you can measure in the visible range. If your solvent also has a color, that's going to be a big problem because that means it also has an absorbance in the visible range. But just to be sure, use your cutoff tables, look up tables of data, and do your measurement carefully. So we saw there that the solvent could affect the peak position. The water and the ethanol give different peak positions from the heptane. So functional groups can also affect the spectrum. So some molecules have all carbons. Some molecules have extra functional groups attached to them. Maybe they have an amine group or an alcohol group or something like that. And these can affect the peak position in the spectrum. So functional groups can enhance the spectra. These enhancers are called oxychromes, and they can be groups undetectable by UV. So some of these oxychromes are not individually detectable by UV. So we cannot get a peak position for them, but they can contribute to the overall expression of the analyte in the UV-Vis expression, UV-Vis spectrum. So we can have different peak movements. So for example, say we have this peak here in the blue. It can enhance the intensity of the absorbance, and that would be a hyperchromic shift. It can decrease the intensity, that would be a hypochromic shift. If you're familiar with osmosis and the words hyper and hypo, then that should be okay. Basically, hyper is increasing, hypo is decreasing. Then in order to get a red shift, we get a bathochromic shift. And then to get a blue shift to higher energies, we get a hypsochromic shift. Don't worry, we'll talk in detail about all four of these and the different chromophores which can actually, or oxychromes, which can actually affect this. But basically, there are rules with regards to how functional groups affect the spectrum. So as I said, an oxychrome is a color enhancing group. They do not have characteristic absorptions in the UV, but they do manipulate or do influence the absorptions of other compounds. So common oxychromes are these. So we have OH, we have OR, so we have alcohols, we have ethers, we have amines, we have other amines, we have other amines, and we have these hydrogen sulfides. So this are the thiols, These are thiols. So these all don't actually have absorptions in the UV, but they can change the peak position of other molecules. So usually they're appendages on other molecules. We'll see how this shift happens in a moment. So oxychromes work by extending the conjugation of a chromophore by sharing their non-bonding electrons. So typically these all have lone pairs. So for example, oxygen here has lone pairs on it. Same here with ether. The nitrogen, hopefully, you know, often has a lone pair. And so all of these have lone pairs on the nitrogen, and sulfur also has lone pairs. So actually it's 2 lone pairs. It's in the same group as oxygen. So there's similar properties. So they can contribute these electrons to the system. Usually it's by extending this idea of conjugation. We'll talk about what conjugation is later. You might have come across it though in other topics, and especially in organic chemistry. So oxychrome effects on spectrum, we've already talked about the idea of hyperchromic shifts. Hyper meaning larger, increases the absorbance. Hypochromic, hypo meaning smaller, decreases the absorbance. Hypsochromic is a blue shift towards higher energies, and bathochromic is a red shift towards longer wavelengths or lower energies. So a hypsochromic blue shift is the removal of conjugation and the change in polarity of the solvent. So if we remove conjugation, i.e. we just have a regular alkane, then we're going to end up with something which is going to be more in the UV. So it's going to have higher energy absorbances. Why is it going to have higher energy absorbances? It's going to be because it doesn't have those pi to pi star transitions. It only has the sigma to sigma star, things like that. Pathochromic is a red shift. So this is caused by oxychromes or chromophores and solvent effects. Hyperchromic obviously increases the intensity, and hyperchromic decreases the intensity of the spectrum. So bathochromic shifts, so these are a red shift towards a longer wavelength. So a longer wavelength, if we recall from a Planck's relationship, corresponds to a lower energy. So a red shift is caused by the presence of an oxychrome or by a change in polarity. So for example, N to pi star transition for a carbonyl compound causes a red shift when the solvent polarity is decreased. So yeah, so when this N to pi star transition for carbonyl compounds, red shift when the solvent polarity is decreased. So when we have a non-polar or a more non-polar solvent, we'll talk about carbonyls later as well. So here's an example of a bathochromic shift to red shift. So say we have this is a UV-vis spectrum of benzene. It has a lambda max of 178 nanometers in this solvent that we're choosing. So here is the lambda max here at this peak position here, where we have a peak position of 178, and you can see this is the highest point of the spectrum. So benzene is this molecule here where we've got 6 carbons in a ring, and they are an aromatic ring, so they can share all of the electrons freely within this system. There are hydrogens at each one of these points, each one of these positions, carbon positions. And then what happens though if we change one of the hydrogens to a amine group? So this is one of the chromophores that we talked about earlier, these amine groups. So this is now something called aniline, and we've seen that the peak position shifts to around about 230, somewhere around about 220, 230, something like that. So there's been a significant peak change just by changing the hydrogen here to an amine, an amine group here. So this amine group has caused a red shift. It's caused this bathochromic shift to a longer wavelength. So it's in fact turned the lambda max from being too high in energy to being in the measurable range. So the addition of the oxychrome, the amine, NH2, causes bathochromic shift. So this is a red shift to longer wavelengths and therefore lower energies. Hypsochromic blue shifts. So this is where the absorption maximum is shifted to shorter wavelengths due to the removal of conjugation. So this is where the oxychrome comes in. So we're removing an oxychrome, or by solvent polarity change. For aniline, the absorption maximum occurs 230 nanometers, as we saw in the previous slide. We talked about aniline as the lone pair on the nitrogen lone pair, or the nitrogen atom, conjugates with the pi bond system of the benzene ring. So what's happening here is that this lone pair of electrons can be shared within the sharing of electrons here in the benzene ring. So it kind of extends this conjugated system, and the longer a conjugated system is, the lower the wavelength will be. So we'll see as well. We'll explain that in a moment why that is. So in acidic solution, aniline is protonated, causing loss of conjugation and a blue shift of absorption max to 203 nanometers, which is more like benzene. So if we somehow add a proton here through our acid-base behavior, we'll lose the ability to share those electrons with the ring, which means that we're removing that oxychrome and reducing the conjugation. And so the system moves towards shorter wavelengths or higher energies. Solvo chromatism, solvatochromism. So this is either where we have movement from less polar to more polar solvents. So a change in wavelength due to solvent polarity is described by this solvatochromism. So positive solvatochromism is a redshift when solvent polarity is increased. So this is positive solvatochromism. So we have from a less polar solvent, so for example, maybe hexane, to a more polar solvent, say water, if it is soluble in both. Negative solvatochromism then is whenever we move from a less polar to a more polar solvent, we have an increase in solvent polarity. Hyperchromic shifts. So this is whenever we increase the intensity of our absorbance. So hyperchromic shifts, the intensity of absorbance maximum, epsilon max increases. So we have here pyridine. It has this lambda max of 257 nanometers. And then the epsilon max for this is 2,750. Then we have 2-methylpyridine here, which is very similar. It's just at the 2 position, so 1, 2, we have a methyl group here. This methyl group then can actually affect the intensity of the absorbance. So you can see here that if we have the lambda max, the epsilon max, so the maximum absorbance at the peak maximum, which is this, we have 2,750. If we add this methyl group, it increases to 3,560, which is a pretty substantial increase, by 25% increase, 25, something like that. But the addition of this has not significantly changed the peak position. That's because it hasn't really changed the conjugation. The methyl groups cannot contribute to the conjugation because they don't have excess electrons which they can donate into the ring system. So the band changes, and we have pyridine here. Obviously, these are the details from over here. So oxychromes usually increase absorption intensity. So like those which cause the redshift also cause an intensity in increase intensity in the absorption maximum. However, it's not always guaranteed that that something that can cause a hyperchromic shift can also cause a redshift in our spectrum, a bathochromic shift. Hypochromic shifts then, so the intensity of the absorption maximum decreases. So biphenyl has a maximum at 250 nanometers. So it has an epsilon max of 19,000. So it's very, very high absorbance. But if we add a methyl group, it causes the ring to twist like this. So you can see here it's flat and pretty much planar whenever it's just the biphenyl. But if we add a methyl group here, because of the sterics involved, so like the space consuming nature of the methyl group, we end up with a twist in this bond so that the rings go from like this, from flat to this due to the methyl group. And so that changes the peak position somewhat. It's not such a big change, but it does massively affect the epsilon max. So it changes the intensity of the absorption significantly. And so the methyl group distorts the geometry of the molecules, and this causes a hyperchromic effect. Why does it cause a hyperchromic effect? Well, because it reduces the sort of the ability for the molecule to share these electrons in its conjugated system. The conjugation is reduced because of this. Okay, so what are conjugated systems? So if we remember back to any organic chemistry we've done, alkanes are covalently bonded hydrocarbons. So they look something like this, where you have carbons attached to carbons in a sort of a chain, like so. Another way of drawing it is like this. This is 5. So this is pentane. So 1, 2, 3, 4, 5 carbons, pentane. Alkenes then are hydrocarbons with at least one double or a pi bond. So here are a couple. So there's an hydrocarbon here, an alkene. So it's also it's pentene this time, one pentene. So it's got a double bond here. We've got 5 carbons, 1, 2, 3, 4, 5. Here we've got 1, 2, 3, 4, 1, 4 pentene, a dipentene. So pent 1,4-diene, I think is the name. So this then is also an alkene. It just happens to have 2 double bonds. But if we put these double bonds adjacent to each other, so right now these are not adjacent to each other. They're separated by 1 whole carbon, so there's no way for these to interact with each other. But if the double bonds alternate, the system is said to be conjugated, and electrons can move along the whole length of the system. So for example, these systems over here are conjugated. So this is benzene that we saw earlier, and this is going to be 1,3 or pent 1,3-diene. So it's still 5 carbons, but it's got 2 double bonds which are adjacent to each other or alternate. So we've got double bond, single bond, double bond. That's an important structural motif for conjugated systems. It's a scene here as well in the benzene. So it's double bond, single bond, double bond, single bond, double bond, single bond, double bond. It goes around and it's a cyclic aromatic, and it's a really stable structure, and it shares the electrons throughout this. So at all points, the electrons can freely travel and move. Here, the conjugated system is just between the 2 double bonds. So the conjugated system goes from here to here. It does not include this methyl. So conjugated systems can be linked by negative charges or lone pairs on heteroatoms. So for example, we talked about this not being conjugated because the double bonds were separated by more than 1 single bond. So it's double bond, single bond, single bond, double bond. So they're not sufficiently connected. And so we end up with an unconjugated system. It does have 2 alkene or 2 double bonds, but they're not close enough to be conjugated. But sometimes we can link these conjugated systems by negative charges or lone pairs on heteroatoms. So we have oxygens here where the lone pairs can be shared, or we can have a carbene where the negative charge can be shared. So the reason why this can happen is because the lone pairs can kind of donate their electron density and share it to kind of connect these 2 otherwise disconnected double bonds. And the same thing happens here where a negative charge really is just excess electrons. So those can also be shared, and that will extend this conjugated system. So I've got a little quiz. Is this molecule going to be conjugated? You can write your answer, I guess, in the chat or in the comments. Okay, so yeah, I think like it's just the fact that it's in a cycle. So it's that's why it's maybe a little bit more complex looking, but it is in fact conjugated. We have here the double bond, we have a single bond, we have a double bond. So yeah, if you said that it was conjugated, you were right. Don't get too broken up about this sort of carbon over here. If, for example, there was no bond here and this was what existed, then yeah, it wouldn't be conjugated. But because it goes double bond, single bond, double bond, it can in fact be conjugated. It's very similar to this actually. It just happens to be that we connected this part with this part and made it cyclic. So it's like what 1, 3. So it's a cyclopenta 1,3-diene, I think is how you call that. Okay, so effects of conjugation. So basically, the more conjugated the system, the lower the energy we're going to have. So, for example, in ethylene here, we have a much larger energy gap. So it's much bluer. It's still, well, yeah, no, it's in the vacuum UV. Yeah. So this is like very high energy. Butadiene then, so that's similar to what we were seeing there earlier with the sort of double bond, single bond, double bond motif. And you can see that the addition of these other conjugated parts, these other double bonds, reduces the energy here between the what would be the highest occupied molecular orbital and the lowest unoccupied molecular orbital. Then we have a hexatriene here, so that can go there, and then we have octatetraene here. So we see that as we increase the number of double bonds, so here we have one double bond. This is not actually conjugated because it needs to have more than one double bond, but still it's got a high energy. So then as we add more and more conjugation to our system, the energy gets lower and lower, so that we reach lower and lower wavelengths, longer wavelengths, and it's more measurable. Lower energy is equal to longer wavelengths. So here are a few conjugation effects on aromatic molecules. So we have these naphthalene rings, we have anthracene, I forgot what this one's called. And so what we can see here is the lambda max is present here, here, and here. They shift to longer wavelengths because of the addition of more and more double bonds. More and more conjugation has the effect that we end up shifting our wavelengths to longer wavelengths, which means that they're lower energies, which probably means that they are going to be somewhat more stable and easier to measure than they would have been otherwise. So increasing the redshift of lambda max with the number of rings. So for example, benzene we saw earlier had a lambda max of 204, whereas naphthalene here has a lambda max, or sorry, yeah, this is anthracene actually. Anthracene has a lambda max of 286. So just increasing the number of aromatic rings causes a shift towards longer wavelengths. These are aromatic rings here because they're cyclic. So effective conjugation, so we see here as well, the more conjugated a molecule is, so you've got, like, for example, here, that's the ethylene, we've got the butadiene, we've got the hexatriene, and so on. We even have this beta carotene, that's the orange color in carrots. It's also a precursor to vitamin A, I think. We've got carbonyl groups here and here. So focusing on these first four, we can see that as we increase the number of double bonds, so from 1 to 2 to 3 to a lot, we see that we change the wavelength from short wavelengths to longer wavelengths. And that also corresponds to this change in absorbance. So the absorbance, strength of absorbance is about 1500, epsilon is 1500 for ethylene. But as we move towards beta carotene, where there are so many more double bonds, we can see that we've maybe like almost a factor of 10 stronger absorbance. Then here is carbonyl. Here is a carbonyl, or vinyl carbonyl, where it's got this double bond here. So here we're capable of N to pi star and pi to pi star transitions, and those have different energies associated with them. And see, the N to pi star has a very low absorbance, and the pi to pi star, it has an increasing absorbance. So basically both of them increase as we increase the conjugation. So increasing the conjugation by adding the double bond here causes there, pardon me, to be a bit of a shift in the pi. No shift in the N to pi star, but there's a shift in the pi to pi star. It's going to longer wavelengths. It's getting a red shift. It's getting a bathochromic shift. So epsilon, then that's going to increase as well because of the effect of this chromophore, which is going to promote the absorbance. So it goes from 900 to 7100, which is an order of magnitude greater. So different conformers can also change conjugation effects. So here's the same molecule, but our same size of conjugated system, but with different structures. So you can see here, it's this is our buta-1,3-diene. Here it is as difference between this is the trans conformer and this is the cis conformer. So these have different wavelengths associated with them. So the trans has got a lower lambda max than the cis. This is the wrong way around. These should be opposite. I've just noticed these should be switched. Okay. Then here, if we add a methyl group here, we actually cause well, we lock in basically the trans, but the methyl group here it won't really change the peak position, but what it will do is it will make the absorbance stronger. As we saw earlier, the addition of certain methyl groups and things can cause epsilon to increase, but it won't really change the peak position of lambda max. The same here, the methyl groups cause a little bit of redshift, but nothing really massively significant. Over here we have, again, similar to this structure, a little bit of a red shift, but really what it's doing is it's going to create a greater value for epsilon. Then we have here, this is a different structure entirely. So this is benzene, and this is hexa-1,3-triene. So the cis conformer has higher potential energy than trans conformer. Homo electrons have less of a jump to LUMO, lower energy, longer wavelengths. So yeah, basically by twisting the molecules, we end up with more separation between the orbitals, or decreasing the energy gap between them. So UV absorption by organic species. So typically when you're going to be using these techniques in your workplace, you're going to be using organic species, and you're going to be measuring organic species most of the time. It's really, really a valuable technique in like pharmaceutical industries, in quality assurance. You do so much UV. Also, you do a lot of chromatography and mass spec. So most absorption spectroscopy of organic species happens above 190 nanometers. And that's because of this end-to-end star transition that we had before, where the problem was that the excitation from that ground state to the excited state was cleaving the bond or destroying the bond. So most of the absorption spectroscopy that we do is above 190 nanometers. So this N to pi star or pi to pi star transition is the one that we're most interested in. It must contain unsaturated functional groups. These are called chromophores, in order for the absorbance to happen above those wavelengths. So typically broad spectra are caused due to the superposition of electronic and vibrational transitions. So remember that within our electronic energy levels, there are vibrational and rotational energy levels, and those are accessible so long as you have sufficient energy. And so that causes a complication of the spectrum. And so conjugation usually causes a shift of the maximum to longer wavelengths. So you can see here that we've increased the conjugation by adding extra rings, and we can see that the wavelength has gotten progressively longer. So saturated organic compounds with oxygen, sulfur, nitrogen, or halogen atoms can be excited by radiation from 170 to 250 nanometers due to the presence of their non-bonded electrons, or atoms, sorry. Yeah, non-bonded electrons. So detecting carbonyls, then we talked about this earlier. Carbonyls are unsaturated systems with N or oxygen, and they can undergo N to pi star transitions around about 285 nanometers, in addition to these pi to pi star transitions. Due to the fact that this transition is forbidden by selection rules, so that's from physical chemistry, it is the most often observed and studied transition for carbonyls. So yeah, so even though this is technically not allowed, there are some things which mean there are going to be some effects, which means that it can actually be measured. It's just quite weak, but tends to be quite useful. This transition is also sensitive to substituents on the carbonyl. So like earlier, we added that double bond, that alkene, that functionality. So similar to alkenes and alkynes, non-substituted carbonyls undergo the pi to pi star transition in the vacuum. So that's 188 nanometers. So the epsilon here is 900, and it is very sensitive to substitution effects. But yeah, carbonyls are another thing which can be easily measured in UV, and they're regularly measured. So here are a bunch of different colored compounds. we have just like the size of their conjugated systems and the sort of the effect that has on their color. So we can see here that this conjugated system is quite small. We get quinone. This is the flavor in, I don't know if you've ever tasted tonic water or anything like that. It's got quite a bitter flavor that's from quinone, which is also this kind of yellow crystal. Allura red, that's a common food colorant used in a lot of jellies and things like that. So that's got a longer wavelength. It's got a more conjugated system. Then a trypan blue, it's used as a stain, as far as I know, for biological studies, biochemistry studies, and things like that. And so trypan blue, it has a really big conjugated system, and so it goes to even longer wavelengths. And so that's the end of that. Thank you for watching.